Sounds good. Okay, it is now recording, assuming everyone hits the big OK button, which sure they will. Welcome everybody to the uh, fifth and sixth code walkthrough combined into one code walkthrough because we had some issues with last week's. But the topic of today is going to be the layers that make up the drand code base, by and large. And then if we've got some time left over, which I think we will, we'll follow on with the next session, which is on metrics and how we gather metrics and use them on drand. Also, I think you may be unmuted, Yulan. I can hear soft sounds of typing in the background, as delightful as they are. Okay, so we've already looked at moments in the other code walkthroughs into some parts of these layers. In particular, the CLI, which I'm going to leave out when discussing these layers. We're going to focus just on the daemon itself in today's code walkthrough. So I guess the way to think about the drand daemon in general is it's a bit of a tree of different dependencies. And at the root of this tree is the drand daemon itself. It holds a bunch of references to some of these other downstream components, which themselves hold references to some other downstream components that they rely on. That's pretty standard for I guess any software application. And the drand daemon itself encapsulates multiple different beacon chains since 1.4, version 1.4. So that means you can have different networks running at different frequencies, running different schemes, and interacting with different networks of different parties, all within the one daemon. So rather than having to spin up multiple daemons in your system, there's some efficiency gained there by using the multi-chain support that we have. So I guess the key part to look at here is that drand daemon contains a map of different beacon processes here that are mapped by their beacon ID, which is basically a string that represents what that what that chain does. So in the mainnet, for instance, we have a default network called default. We've got a fastnet network that's recently been soon to be sunset, and we've got QuickNet. Those all run different schemes. Some of them run different frequencies, but our drand daemon houses all of those. So underneath the drand daemon, it more or less organizes starting the application, stopping the application, and setting up some of these dependencies. It's the dependencies then that do a lot of the core work. So top of our tree, drand daemon, first branch down goes to a bunch of different beacon processes. So let's dive into the beacon process. What? Rather large, it's slightly smaller. So not to be confused with operating system processes, it doesn't literally spawn its own process. It still lives inside the drand daemon process. Although it's kind of analogous to a process in that there's one running per beacon ID, and it manages kind of all its own stuff. So each of those has a key pair, chain hash, a group if it has performed DKG. And these are sort of not that important. A more important point to note here is it's got a couple of different stores. They form the next set of connections in that tree. Each component ends up storing its state in a store, and that's a theme that we see in some of the other components as well. And in fact, the beacon process has two different stores. It's got a key store and a chain store. The key store, as it may obviously sound from the name, stores all the key material. So public keys, private keys, and it basically represents some file store on disk that contains any keys that you generate. The chain store then stores everything that's beacon related. So that whenever you aggregate a beacon, you've got all the partials from other nodes that you can use for aggregation. When you've actually completed the aggregation process, you store the full beacons in there, etc. There are some other bits that are not necessarily in the scope of our little tree we're imagining here, but one thing we will jump into here is this beacon handler. So the beacon itself, again, is slightly abstract data structure. It doesn't do quite a lot of the actual nitty-gritty of aggregating the beacon. That's done in the handler here. So we can imagine that's the next node down in the tree. The beacon handler does a lot of the heavy lifting with regard to all the cryptographic operations, aggregating the beacons. It also monitors a threshold through this threshold monitor to tell whenever it has tries to interact with other parties and it fails to do so. We can work out whether what the state of the network is in health wise. That'll come into the metrics part later, so we might come back to it. And then the handler really is like a leaf node in the tree to some degree. It it's doing the good stuff. We it processes the partial beacons that we see here, and ultimately it aggregates them and stores them in the beacon store. Um, yeah, get started. Every time, for instance, we do new distributed key generation, we stop the handler and start up a new handler at a given time. So these are sort of fire and forget um, between different epochs of distributed key generation, but they're owned by one beacon process, which gives us sort of individual mapping between daemon to beacon process to handlers. So we can kind of see the nature of the relationship between all these different parts. So those are the key points really for everything related to the beacons, so aggregating the beacons. We touched on the distributed key generation, and as of V2, which this is a bootleg version of, this is not actually the master branch just yet. This is still on the develop branch, but will very soon make up drand 2, coming to a threshold network near you. We kind of identified that creating different beacon processes per beacon ID was slightly wasteful in terms of resources. In some sense, right now we only run 3 beacons in mainnet, so there's not a massive amount of overhead there. But theoretically, if you wanted to take part in dozens or hundreds of networks concurrently, you would end up using quite a lot of memory if you had to spin up a beacon process and all its dependent parts and different stores for each of them, um, all in one drand daemon. So with that in mind, with the DKG process, rather than having multiple processes for each of the beacon IDs, we have one DKG process, which will take the beacon ID as a parameter and kind of do the business based on that. So the DKG process, as part of the drand daemon, like you might imagine, does everything related to the DKG. So it keeps reference to a client, it gets some other information from the drand daemon, which itself doesn't hold. It keeps a log of everything that's in flight. Oops, these damn tooltips. Everything that's in flight for DKGs that are going on to ensure that we can have multiple DKGs across multiple networks in different states happening at the same time. And like we've seen in the beacon related stuff, also it has its own store, which lives on disk. Because it's in the same package, we don't have a lovely DKG prefix to make it obvious what it does, but in the context of DKG package, this makes a lot of sense. I guess another benefit to this is that this DKG process is kind of a leaf in its own, other I suppose, in the stores that we've talked about, but there's not the same hierarchy between process, handler, etc., etc. This just hands off to the existing Kyber DKG, and yeah, a magic happens. If we didn't go into the handler much itself, but in essence, I don't know we did, sorry, we already looked at threshold monitor, never mind. Okay, so we skipped briefly over these things. These, I guess, are dependencies of kind of a lot of different things in the system. These are the different networking dependencies that the drand daemon creates upon start and shares between the different parts of the application. So this private gateway is basically for any communications that happen between members of the different networks. So if I want to aggregate a beacon, if I want to start a DKG, this goes over the private gateway. So as logically follows, it gets past the beacon process and passed to the DKG process, and they do their necessary business with it. I guess the benefit of having that is, firstly, in terms of compatibility, we our partners who are running drand nodes might be slightly more willing to break backwards compatibility because they're always running the bleeding edge of drand technology, more or less. Additionally, we have quite tight firewalls between different nodes in the network. So we run an IP allow list between different nodes. So as a result, traffic coming over the private gateway can kind of be logically segmented as that's going through the firewall versus public gateway traffic where, and this is also an optional parameter, you don't have to have a public gateway, but if you wish to serve your randomness from your node to the world or to a CDN or to a relay or something in front of a drand daemon, you spin up a public gateway and basically anybody can query that endpoint for traffic. Uh, a sort of additional point here is that internally we use gRPC, so that's Google's magical RPC framework that's uses protobuf as a data formatting and parsing tool, you might say, which is slightly more efficient, maybe depending on your benchmarks, how you do it. It's probably definitely more efficient than HTTP, but I'm sure there are other options in gRPC. The public gateway, however, we don't run a gRPC public gateway anymore. That's just HTTP. And I guess there's libpdp and stuff as well. This control listener plays into this relationship, this tree relationship, because we expose some different functionalities on the control port for people internally to run on their own node. So, for example, if I want to sync my node with a new chain, maybe somebody spun up a new drand network, I want to join, but they've had a couple of DKGs already, and I'm late to the party. We don't want anybody from the outside world to be able to start syncing our node, because obviously it can be quite CPU and memory intensive. Additionally, we don't want just anybody in the drand network we're joining to be able to do that as well. So we have a separate port just for things that we want to do internally. So I log onto some machine, I run the requisite CLI tool that interacts with the control port, and then I run some of these everyday tasks. How this plays into the tree structure is that oftentimes we want to do something with one of those downstream dependencies. The beacon process might want to do something, or in some of the stores might want to do something when it comes to, for instance, syncing things. So the drand daemon owns this control listener and delegates some of these functionalities down to lower level listeners. As well as that, we do use channels for some communication between these different parts of the tree. I think there's always a tension in software development in deciding what objects, structs, data structures own different pieces of data and how those communication lines fly between them. Obviously, if you can bi-directionally connect everything to everything, i.e., A has a reference to B and B has a reference to A, your project can quickly turn into spaghetti. So it's quite important to decide who is the owner of certain data and who just, where does other parts of your system read that data from and how do they do it. So we use channels in a lot of places to decouple parts of the system. One example, this completed DKG's channel is written to by the DKG process. So whenever it completes all the magical distributed key generation packet switching mayhem and ends up with a group file with a distributed key and all the other parties of the group, that gets funneled through this channel all the way to the beacon process, rather than the beacon process itself having some reference to the DKG process and doing other kinds of arcane magic to get the stuff at once. We just use a channel and it's all very decoupled and lovely. So I made a reference a moment ago to the sync manager, and it's a slightly unusual case in that it doesn't live in this drand daemon itself, although it lives deep in our stores. Now, our store implementations are actually the topic of another code walkthrough. In fact, possibly the next. Yeah. In fact, the next code walkthrough. So I'm not going to go into excruciating detail on the sync manager and the stores and how they work. But the long story short is that we take some base store and we wrap it with different functionalities. So we get in the end a store that satisfies many different interfaces and could do different things, such as storing callbacks, being a file store or a cryptography vault, etc., etc. or in the case of a chain store here, having a sync manager. Um, this sync manager then allows the node when it gets behind on beacons. When it gets behind on beacons, it can sync them from other parties in the network, but naturally that has dependency on what network it's in, what parties in it network. So it kind of has some relation to the beacon process, although it's actually inside the store. So that is kind of the slightly complex relationship between some of these key components here in the drand daemon. Um, the sync manager is something that we, far off distant future when we've got money and time and we would like to refactor it. I think in part because it's a little bit weird that it's kind of tacked on to a store when it has so such great importance, I suppose, to the beacon process. And additionally, it's a little bit uh, overused is a wrong term, but in essence, your node can start doing a sync on its own if it realizes it's behind. But you can also tell your node to do a sync if, for example, you want to join a network like we discussed before. So it's overloaded and it does multiple things, and sometimes that makes the code pass a little bit confusing. Um, but nonetheless, that is state of play with regard to these dependencies. Let's see if there are any other interesting dependencies here on the drand daemon. Drand handler sounds really exciting, but again, it's just for HTTP related stuff, so not that exciting. Those, yeah, that makes up basically everything that's in the daemon itself. Additionally, we have clients and relays that we discussed in a previous code walkthrough. I think there's another one on clients at the end. So I'm not going to go into the clients. And actually, in version 2, all these clients and the CLI will be torn out of the core drand code base and put into their own separate libraries so they can evolve at a slightly different rate and not clutter up different parts of the code base here. So does anybody have any questions on the layout and relationship of the different components in the drand code base? Okay, wonderful, wonderful. That's glorious silence. With that in mind, then, I shall move on to the metrics part of this code walkthrough. So obviously, when running any network in production, it's super important to have very good insight into what's going on in the network, how data is moving in the network, what's up, what's down, what's sideways. That's all important. And thank you to Mario Camus on the within the Protocol Labs who implemented, I believe, the initial version of metrics that we use in the drand code base now. So what drand uses is a tool called Prometheus. It's kind of the industry standard for doing metrics related things, has been since the dawn of time, or at least several years. So um, each node uh, hosts an endpoint or a port basically with which other nodes in the network can pull metrics from it by Prometheus. Prometheus is more or less a data format at this stage and a kind of related libraries around it, which allows you to track movement of some data within your system over time in a nice text format and allows other nodes to access it via port and pull it from you. That's one thing that makes Prometheus different to some other metrics libraries where they are push, i.e., an event happens, I push my metric to some centralized or decentralized service, and it gets aggregated elsewhere. Prometheus is the other way around. You come up with some metrics, and people pull them from you when they want to do something with them. So it's fairly simple. It's all run-of-the-mill Prometheus stuff. We create a bunch of different Prometheus data types, metrics types, in this case, like a counter vec, for example, counts all the number of requests received, failures received. Yeah, gauges allow you to group some different parts of the data together. This is histograms allow you to, funny enough, draw histograms. Um, this is all pretty run-of-the-mill stuff in terms of Prometheus. I'm not going to give a deep dive on how to use Prometheus. But the code itself is instrumented with Prometheus in a lot of the key parts. So at any time, you kind of know what the state of your node is in terms of resources used, in terms of how it's seeing other nodes in the network and what kind of timing it's taking to um, aggregate beacons and such like that. Additionally, something which I kind of forgot about actually, but I suppose it'd be a cool moment to mention it. If I can remember where, I think it must be in the README. We've also optionally, I mean, nobody is running it. Is one of our nodes running it? Anyhow, we have also instrumented the binary for open metrics. That is rather local rather than in the previous example. Prometheus allows people, well, you to monitor your node and also you to monitor other nodes in the network if they expose a port to you. But we also have an ability to actually measure code paths within the code. For instance, seeing exactly where your time is being spent in a particular request, for example, you can see a little flame graph of which function calls are taking long, which where data is being stored and what's using up all your RAM. I thought there was a, let's see, open metrics. Oh, dear me, disappeared. Met Open telemetry endpoint. Sorry if I can remember the name. So yeah, we've got a Docker Compose file for that and Docker Compose tracing. So you can just spin that up alongside your drand daemon, and Bob's your uncle, Fanny's your aunt. You'll have lovely insight into everything that's going on. This also uses like an open standard for telemetry, so um, uh, you can use open source and probably closed source tools to analyze that if you want. This, I think, comes with a fancy UI tool, so you can visualize it already, which is nice. As big thank you to Florin from Arden Labs who worked on that, and yeah, it gives us we've used it already to identify certain things like how long it takes us to aggregate a beacon under what kind of circumstances. In future, we'd love to test bigger networks and get a very clear idea of where the limits are and what is the limiting factor for big networks. Pro tip, it's a DKG apparently. So Elia, once you've got the DKG, can support thousands of nodes. We're super hyped for it. In terms of how we actually monitor the network on a daily basis, I'm opening Firefox, and I haven't checked what I've got open here, so let's hope it's nothing crazy. Oh, it's a blog post, lovely. So we have a couple of Grafana dashboards that we whipped up. The first one, let's go to the ceremony dashboard. When we do a ceremony, obviously, firstly, that's probably the riskiest time in the DRAM network's life is when you're running a ceremony. Anything anything can happen, anything can go wrong. If it goes wrong, fires break out and people get in trouble. So this dashboard gives us a little bit of insight into what's going on during a ceremony. In particular, we can see what versions people are running from. Hopefully nobody's running from any DRAM versions, but we can see which DRAM versions they're running. We can also see how many connections they have to other nodes in the network. So we've had some examples in the past where nodes in certain regions don't have good connectivity to other regions for technical or political reasons. We can identify that this node can't talk to these other three nodes in this region. And luckily, drand codebase accounts for that and does some cool packet routing and gossip protocol and stuff. But we can see that and identify if somebody says, "Oh, I've got an error with this node," we would have to know whether it's their node setup or the network setup or something else. We can see all the different nodes are up, obviously. We can see some other cool things like how close to threshold we are, a different DKG state, which in the future, as of DRAM v2, this dashboard will need updated. I better add that to my to-do list. in order to show exactly which state in the DKG has been reached by different parties. Also, we can see the different host view of the world. So which rounds they've aggregated, how long it took them to aggregate that. That allows us to track, um, firstly, who's participating in beacons by and large, who is up to date and synced with the whole network, um, and also gives us some insight into where in the world gets the beacons first or at what time. I mean, in principle, multiple people could be aggregated in the same beacon in different places at the same time, but it's interesting to note, for instance, IPFS hosts who are based in China have a slightly higher beacon discrepancy than, for example, Chainpoint, who uh, we're in the US, but don't quote me on that. But anyway, long story short, different people have could have slightly different beacons or the same beacons at a slightly different time. Additionally, nobody at the moment is running a memdb backend. That's a hard one to say for drand. And memdb backend is basically, rather than storing the data in a file store on disk, you just sync the latest beacon when you start up, and you keep it all in memory, which people with constrained resources could be beneficial. Potentially, we would like to see they've got missing rounds, or they maybe are missing some rounds on the way, or people are behind. I mean, this has been a real killer dashboard for seeing that people are lagging behind. For example, for mysterious firewall reasons, we've had some parties who got their machine changed, but the firewall was reverted to an old version. They couldn't connect to anybody, and they were 10 bazillion rounds behind. And yeah, this dashboard's killer for seeing that. The source for this dashboard is actually not available to the world. Though I don't think in principle there's any reason for that. I just think there might not even be a source for this dashboard. I think it might just be handmade by Lucier in Grafana itself. But people want it. That's a change we can make happen. Additionally, we have another network health dashboard here that just gives some slightly different visualizations of some of the same data. So we, for instance, see here the total number of requests. It's kind of going through our infrastructure through AWS, but I imagine a lot of people, at least providing a relay, might already or might want to do something similar. Also, CloudFront for requests error rate. This is just a fancier graph of the time discrepancy we saw in the previous dashboard. Again, interesting to note here that different mainnet nodes have different discrepancies, sometimes quite wildly. So, for instance, our node in Asia aligning with what we saw in the previous dashboard. Oh, my screen sharing is paused. I'm sharing the wrong screen. Oh no. How long have I been sharing this dashboard and nobody's noticed? That is quite unfortunate.
Oh, you were showing the dashboard.
I was
Oh.
sharing the dashboard, so that's
Hmm.
oops. Well, hold up. Let
Yeah,
me.
we're looking at the Docker compose tracing at the moment. So
Okay. Well,
okay, that makes more sense now.
yeah. No, so here was the ceremony dashboard that you all missed. Hopefully you can remember everything I said about it, but in long story, we've got the connections that people have to different nodes. You can't see my hand waving, so I'm waving. It's the version that people are running. Uh, you can see delightful other things, so like a nice little matrix here of ooh, everyone's connected to everyone. We can see the threshold, beacon discrepancy, what runs they're running, etc., etc., etc. Reshare state. Here is a slightly prettier, in my opinion, dashboard, but I had to make it, so I would think that. This is some details on AWS land. This is some details more on the network land, so we can see the threshold over time. Let's see if we can get some slightly more spicier info here. Here we've seen some nodes went down temporarily, very brief moment. Luckily, they didn't reach threshold, which is up here. That would mean that the network stops aggregating beacons. That would be scary. We can see additionally which nodes went down in this period. So Cloudflare went down very briefly. Also CBOT. The source for this dashboard also isn't It isn't in the wild, and I made it by hand. But I'm sure there's a way to export a JSON file to make this happen. Um, if anybody would like it. Additionally, we also use InfluxDB, which pulls Prometheus metrics and kind of brings up similar dashboards to these for things like CPU and memory and such. It can be obviously super useful to monitor that to see um, what circumstances are affecting your DRAM node in what ways. So we've noticed in the past we found a bug in the sync process because we identified that when nodes were quite far behind, their memory would and go routines spike, and eventually they would get killed. And we realized, this is because of the sync. Are there any questions on monitoring a DRAM node? Sweet silence. Lovely, lovely. Okay, well, that is all I have on monitoring drand and the layers, at least this very moment. Yeah, that's all I have, guys. So thank you very much. If you have any other questions, you can always drop them in the drand dev channel or some other channel that might be more appropriate, but I think drand dev would be the best one. Oh, hold up in chat here. Can you see, hello, Karina. Can you see from here the connections of each node? Yeah, so on this dashboard, you cannot, but on the ceremony dashboard, yes, we've got this lovely matrix here that, yeah, that can tell you who is connected to what other nodes. Let's see, we've got some transient failures here. That's kind of interesting. I wonder why ChainSafe can't connect to ATA network. Emerald Onion can't connect to IPFS Force. Emerald Onion run a Tor gateway, so I'll leave you to figure out the reasons why they might not be reachable. Dedis, interestingly, can't reach Vetus. I mean, of course, these could just be, fallacies of the network that, I've forgotten the whole list, but there's a great list of fallacies programmers believe about networking. And then one of them is, the network's always stable, and a whole bunch of other interesting network related fallacies that you should read. Any other questions? Of course, there are additionally CLI tools for getting some insight into these network connections too. So, for example, you can run the util check command, and you can run the util status command. I always forget which one's which, but one of them will ping each node and ask it to ping all the other nodes and tell you their view of the world, basically. Which is quite useful again for building up this sort of this kind of matrix of who can talk to whom. That there are the dative case. Oh my goodness. Also, coming back to the Prometheus stuff earlier, you don't have to expose Prometheus endpoint as a metrics endpoint. Most people do it because it helps us build lovely dashboards like this. And it's super helpful. But of course, if you don't want that, if you don't want the open telemetry, it's not on by default. Don't expect that if you were to spin up your own DRAM network today, the DRAM team will be taking your data and selling it to big data brokers. I mean, we wouldn't get your data in any case, but even if you did enable telemetry, but it's not on by default. So fear not. Any other? Jeez, I'm so confused by the Zoom overlays. Any other questions, concerns, or thoughts? Well, thank you to everyone who came. Thank you to everyone who's watching this in the future on YouTube, or preferably some kind of IPFS or Filecoin driven distributed streaming service. I wish you good luck in grokking the layers of the DRAM code base and of monitoring your future DRAM network or DRAM node if you wish to join the LOE and run a node yourself. The next DRAM code walkthrough will be on the DRAM storage and sync functionality, which we touched very briefly on today, and we touched somewhere near the start as well, and the CLI talks. That's going to be by Yolan. So I am reprieved for, well, at least I hope so. I didn't check the schedule, but I'm pretty sure that's the Yolan talk. So I'll be reprieved from code walkthroughs to relax as always. So thank you very much, everyone. The next one is in 2 weeks. What are the dates here? 2 weeks, which is 30 days. How's September, June, November? That is going to be the 12th of September. So good luck, have fun, and don't do anything I wouldn't do.
Awesome. Thanks.